Hey you guys, I've got another mini lesson for you. This is on intermolecular forces of attraction still, and it's on molecule polarity. So I recommend that you have your capillary action lab handy. This will help explain some of the answers that you will need to provide for that lab. Another reminder is table S in your reference tables is a good place to look up electronegativity values for elements. Okay, and what I have on this sheet here, well, you saw my first mini lesson, hopefully. This is a follow-up to the first one. This will help us with the capillary action lab. And it will help you in some of the boiling points in IMF worksheet that some of you have been working on so far. So here we go. First of all, molecule polarity is divided into two groups. You're either a polar molecule or you have a non-polar molecule. Polar molecules, if there's any hydrogen bonding potential, that molecule is always polar. If a molecule has an OH group, it is always polar. And there are several examples from our lab that you will see shortly regarding this. Also, if a molecule lacks molecular symmetry, it will be polar. On the other hand, nonpolar molecules are diatomic elements. They are the monatomic noble gases. Hydrocarbon compounds, they only contain hydrogen and carbon. They are all nonpolar. And nonpolar molecules have molecular symmetry. So a little bit about molecular symmetry. My cute little penguin here has molecular symmetry. If I split him in half here, both sides are symmetrical. On the other hand, this beautiful shell is asymmetrical. If I split it in half here, one side is different from the other side. So think about molecule symmetry in terms of that, okay? And if you think about it, polar molecules are going to have a slightly negative end and a slightly positive end, and these are some of the factors that may be present making it polar. Okay, let's look at some more examples. If I can get there. Here we go. So examples of nonpolar molecules. As I mentioned, all diatomic elements are nonpolar. You can look at the electronegativity values. This hydrogen has the same amount of pull on the electron as this hydrogen does. And this dash represents two electrons, one from this hydrogen, one from that hydrogen. They are sharing that, and they have equal pull on those two electrons. They're the same type of element. Therefore, this would always be a nonpolar molecule. The same applies for chlorine and other diatomic molecules. Okay, some more nonpolar molecules. All noble gases. This is the chemical formula for neon. That's it. It's got equal pull. It doesn't even want to bond with other elements. Hydrocarbons. Here is one example of a hydrocarbon. This happens to be called ethane, and you will be learning how to name and write these types of formulas as early as next week. So hang in there, it's coming. But you will note, we can look at all of the electronegativity differences here, but the bottom line is this is a symmetrical molecule, and there's even distribution of the electrons between those atoms. Now this one's going to challenge you a bit. We will talk more about it in the future, but this molecule, this is carbon dioxide. You will learn about its bonding. It happens to have double bonds. That means there's 4 electrons sharing in here. But it has what we call a linear shape because there is an equal and opposing pull for the electrons. So the oxygens, same type of elements are here, equal and opposing pull for those electrons, and therefore it cancels out any dipole potential. Therefore, this molecule is symmetrical and it's nonpolar. Okay, let's look at some polar examples. A polar example and a nonpolar example. Carbon tetrachloride is a nonpolar molecule. It is another example of a symmetrical molecule because there is a pull in all directions of those electrons towards the chlorine, and it in effect cancels out any dipole. On the other hand, we've talked about water several times at this point. Water has this shape, it's called a bent shape. It's got a clearly negative end and clearly positive end. This is definitely a polar molecule, and the electrons are attracted towards that oxygen more than the hydrogens. Therefore, it is asymmetrical. And by the way, it has hydrogen bond potential. I know that's a little small there. So that's another characteristic of polar molecules. All right. A little more on different polar and nonpolar molecules. If we look at this example, we have carbon with all the same type of element surrounding it, fluorines. Fluorine is the most electronegative element, has a 4.0 value, and it's pulling pretty strongly those electrons towards it. But the fluorines are all spaced out and creating what we call a symmetrical molecule. So overall, the molecule is nonpolar. On the other hand, this molecule has the hydrogens and only one fluorine. And again, that fluorine has great symmetry. I'm sorry, I misspoke. That fluorine has great attraction for electrons, and therefore you're going to have a net pull of electrons towards that fluorine. It will be a polar and asymmetrical molecule. Okay, let's talk about our OH group examples. This is from part 2 in your capillary and polarity of molecules lab. These are what the viscosity rods contained. The red, the green, and the blue. And I forget which colors they were. But bottom line is, once you have an OH group, one or more OH groups, these are going to be polar molecules. These are actually all examples of a group of organic compounds known as alcohols. You will learn more about them in the future as well. But for now, suffice it to know that this oxygen is pulling electrons towards this end of the molecule. Likewise, here and here. And in this case, all 3 in a row are pulling electrons over here. So, which one of these 3 is most polar? I'd like to call on Hudson right now, and I would like to think that Hudson would say glycerol. Excellent job, Hudson. Okay, so always remember, every molecule on this planet has attraction for other molecules, but polar molecules have a much greater attraction than nonpolar molecules. Okay, and that concludes my mini lesson for now. I hope that helped you. And please always know we will be looking in greater depth over the coming days on this topic. Bye.